Hello everyone. I am here to solve few physics problems which you can enjoy and you can increase your interest in physics. Look at question number 18. In figure, a rectangular conducting loop of width L and resistance R and mass M is hung in a horizontal uniform magnetic field B that is into the page and that exists only above the line A that you can see in the figure. The loop is then dropped. During its fall, it accelerates until it reaches a terminal speed v. Okay, the value of v is given by one of the options shown in the figure. Fine. Let's try to solve this problem. Okay, so here it is given that there is a rectangular loop. Okay, this is rectangular loop and width of the loop is L and its mass is m and resistance is r, which is in a uniform magnetic field, and let us say that exists only up to this line E. Fine. Now if you drop this rectangular loop, what happens? Initially, uh, because of gravitational force mg, the loop starts to move downwards with an acceleration is downward, so its speed increases. As it starts to move downward with some speed, say in a magnetic field B, which is into the page, now a conductor is moving in a magnetic field with some velocity v. So therefore, because of Faraday's law of induction, a current induces in the loop. Okay, so in which direction current induces? That's a question. Now, as the loop moves downwards, the magnetic flux through this loop decreases, and according to Lenz's law, the EMF should be induced in such a way that it tends to oppose the decreasing magnetic flux. In other words, the current should induce in such a way that it should support the external magnetic field B. So therefore, in order to support the external magnetic field, the current should be induced in this direction, like this. Okay, in a clockwise direction, so that this current is into the page. Now there is a magnetic field and there is current in a conductor, so you know that a magnetic force fb vector, which is equal to I into L vector cross B vector, which acts on the four arms of the loop. And you can see this if you look at this upper arm, current is in I cap direction, magnetic field is in minus k cap direction. So put I cap cross minus k cap here, which gives you j cap. So therefore, magnetic field on this is upward fb, which is equal to I into L into B. Correct? Similarly, here there exists no magnetic field. However, current flows through the wire, but there is no magnetic field, right? So therefore, no magnetic force acts on this arm. And here the currents are magnitude wise they are same, but their direction is different. So magnetic force on this arm cancels the magnetic force on this arm. You can easily show that using the same formula. So therefore, in effect, there is only upward magnetic force, which is I into L into B. Fine. Now, as the loop descends, as the loop moves downward, its velocity, because acceleration is downward only, its velocity increases. With increase in velocity, flux also decreases quickly, So magnetic field, induced current also increases. So this increases the magnetic force Fb. So therefore, initially the downward gravitational force is more, Fb is less. As it moves downwards, mg however remains constant, but velocity of this conducting loop increases. Because of that, I increases and hence Fb increases. However, the net force on the loop is still downward only, and hence the loop's velocity increases continuously in the downward direction. Because of this increase in velocity, I further increases and hence Fb also increases. A stage is reached when mg and Fb are equal in magnitude but opposite in direction. At that instant of time, net force on the loop becomes zero and its acceleration becomes zero. At that instant, the loop has reached its maximum velocity. After that, it continues to move with the same velocity because the forces on the loop is now zero. Net force on the loop is zero, so it will not remain at rest there, because before reaching the zero force condition, it has some velocity, right? So therefore it continues to move with the same constant velocity, and that maximum constant velocity is what terminal velocity is. So therefore the key point here is terminal velocity means the maximum velocity, and at that velocity the acceleration of the entire loop is zero. So therefore let's find out what is the terminal velocity. And we know that the terminal velocity is a constant velocity, and which is also maximum velocity. If you write the equation of motion of this loop, it looks like ILB minus m into g equal to 0. Actually I would write mass into acceleration here, but acceleration is 0, that's why right hand side is 0. Now we know that induced current is given by induced EMF in the loop BL into V divided by resistance of the loop is R into L into B minus mg is equal to 0. And I have written this condition when this equation when the loop has reached the maximum velocity, correct? Therefore this V is nothing but terminal velocity. Now if you simplify this V, you will get V is equal to mgr upon B square L square. So this is the terminal speed, the maximum speed reached by the loop. Okay, so therefore the correct option here is option 2, right? Thank you.